Okay, g'day, my name is Brendan Gregg, and I'm going to be covering flame graphs on FreeBSD. And yesterday I introduced myself, so I'm going to skip the introduction slides, and I also introduced myself briefly this morning, so I work at Netflix on performance. I'm going to cover genesis of flame graphs, their generation, and then different types of flame graphs, so CPU, memory, disk, and off CPU, and then chain graphs and new visualization types. So the genesis of flame graphs. Telling a story can really help explain something complicated like this, and the problem I had was that I had the same MySQL load on two different hosts. These were two different operating systems, and so one was Linux and one was SmartOS. And it turns out on Linux it was running 30% faster than SmartOS. This sort of comparison is something that many of us in the FreeBSD community may face from day to day when people are comparing Linux to FreeBSD. And so I had to quickly understand why performance would, this application would burn 30% more CPU just because it's not running on Linux. CPU profiling should answer this easily. I like CPU issues because profilers are great. I can just sample stacks at a certain interval. It's lock contention and wakeups and priority inversion. They're the hard issues. CPU issues are great. So I used dtrace, profiling stack frames. I did actually profile it at almost 1,000 hertz. I don't really do that these days for user level stacks. I usually take that down. Anyway, dtrace one-liner, set the user stack frame depth to be up to 100. If I'm MySQL daemon, aggregate on the uStack, and then count. And what dtrace will do, and you can do this on FreeBSD, is it is going to frequency count the entire stack as a key, which is fantastic. Instead of, many profilers will dump events, and then you have to post-process the file. PMCstat is great. I love PMCstat, but it's one of those profilers that currently dumps events one by one, and then you post-process the PMC log. Dtrace can do in-kernel aggregations, so it uses that entire stack as a unique key, and then summarizes that in kernel using per-CPU buffers for efficiency, and then when you dump the output, it's printing out the stacks, and beneath the stack it's got the count. So I saw this stack 4,884 times. I saw this stack 5,530 times. You see the same stack so frequently because software runs in loops, and when it's in the loop, the same stack is on CPU. Great. So all I have to do is do a profile on my system with dtrace, and then another profile on the system with Linux, and then spot the difference, and I'll explain this 30% CPU delta. The problem was, this output is already compressed. That's what I'm stressing, is the fact that it's already done the frequency count. This text-based output we're looking at is already reduced. There were two problems with this. The first problem is, I know how many counts I had in total, and dtrace has printed them out in order. I elided all of the output because there'd be many screens. The last stack, the count, based on what I was doing, that's less than 2% of the samples. So even though that stack is most frequent, it would be a mistake for me to think that that was the 30% delta, because if I count up all of the samples I've got, that's less than 2%. That is the problem. I have over 500,000 lines of profiler output, which is already reduced, which is already summarized. I wanted a way to show people what this looked like, so I loaded all of the profiler output into a HTML file just so that a browser could display it, and came up with this image. This is actually all of the profiler output from MySQL. That's the size of one stack. The last two stacks I had on the previous screen, can't really see, but they're way down there. And that's just the unique stacks. The problem I had was I have to compare this gray featureless square with another gray featureless square that I had from Linux's profilers and understand the 30% difference. And I have to do this as quick as possible because we could lose the customer. And so this is to me, was an impossible problem, and I started playing with other visualizations in order to get my head around this data. That's a flame graph of the exact same data. That was the gray featureless square. And so the flame graph and I've got it loaded. With the flame graph, on the y-axis is the stack depth, and on the x-axis is the sample population. And I went through these briefly yesterday. The sample population shows all of the samples so that the wider a frame is, the more frequently it was sampled. There's a few great things about this. First thing is, I can see all of the data at once. So it's not this gray square, it's not just loads of text. That's all of the profile data. Some of the stacks are so infrequent, they're printed very thin, and I can't read the text. And at the first pass, I don't want to, because the text that you can see, if it's wide enough to read, then it's important enough to read. So as a way of just the nature of the visualization, the way the text has been included horizontally, the way it elides a lot of the text because it just doesn't fit is fine with me, because I care about, this is the stacks that are burning CPU. So I'm burning CPU in join exec, and I'm burning CPU in file sort, and I'm burning CPU in do select, subselect. And also, this is generated from a Perl program that I put on GitHub. It takes the profiler output and emits a SFIG. It also includes a little bit of JavaScript with the SFIG, so if you load it in a browser, you can mouse over it. So if I mouse over join exec, it tells me straight away that join exec was in 78% of the CPU samples. And so as a performance engineer, I can move around this interactively and quickly quantify where my CPU time was spent. Using flame graphs, I was able to solve the problem by Friday. So that was great. Comparing, and I did the same thing on Linux. So I was able to compare two flame graphs. The difference between them actually showed compiler optimizations. Even though it's the same version of MySQL, I could see that on the Linux flame graph, the hot code path was missing a frame, but on my SmartOS flame graph, the same code path was taller. It had an extra frame in there. And when I brought up the source code, you could see straight away that this was eligible for tail call optimization because it was return and then function name. And so then it's like, well, I should just check compiler options. Like, why didn't I check that sooner? And then found out that the make file had -03 if you're Linux, but if you're rest of the world, you can suffer and have -01. So I feel bad about that because I should have checked that sooner. But anyway, the problem was solved. I'd gone down the path of thinking a CPU profile was going to solve this, and the flame graph visualization helped me digest all of that data, even though I feel bad in the end about what it was because it was actually trivial. I've since used flame graphs to solve many, many issues because it's a great way to visualize tons of data. You don't always need flame graphs. So sometimes the profiler output is pretty simple because you just have one giant thing that's hot on CPU, and when you're looking at the last sample that dtrace is giving you, that's like 98% of the samples is here, and you just don't need a flame graph. It's done. So don't always need it, often you do need it, and it works well. FreeBSD is very interesting because you have dtrace and PMCstat, and they both can generate all sorts of different flame graphs, which I'll go through briefly. So to define the flame graph, the boxes are functions, and they visualize a frame of a stack trace. The y-axis is the stack depth. The top function led to the profiling event. So it's whatever is at the top, that's what's on CPU. Everything beneath it is the ancestry. The colors that I've done for the standard flame graphs like that, like this guy, are picked at random just to make it easier to see, just to make it easier to browse, more visually interesting. It also separates out towers. So you can see these are all different towers rather than just being the same frame. So very simple, just randomized. But you can use color hue for other interesting things as well, which I've been doing, which I'll get to. The presentation of flame graphs, all threads can be shown on the same graph. You can also do multiple distributed systems. So nothing's stopping me from collecting a CPU profile from an entire cloud or many servers and then just putting it all together as one flame graph that you can mouse over. Interactive, you can actually draw them upside down. Facebook implemented flame graphs but did them upside down so they look like icicles, which is fine if that's your preference. And of course we can use colors for other things. So generation. This is the just a couple of instructions for generating these on FreeBSD. Very simple. Git clone the FlameGraph software, or you can go to GitHub and just download the zip if you don't have Git installed on a machine. Sometimes I've had to do that. And then, if dtrace isn't already loaded, here's an example of doing a kernel FlameGraph. So we're just setting the stack depth, profiling at 197 Hertz. arg0 for the profile provider of dtrace is tested. That's the kernel program counter. So I only want to capture a kernel stack if it's kernel code on CPU. You can do the same thing for user level stacks. So that just samples for 60 seconds, and then I have a program stackcollapse.pl that takes the format and it generates output that looks different. So, in fact, I was just doing one, so here's the output of dtrace on a system. On one of the Netflix OCAs. I just did this like 20 minutes ago. That's the output of dtrace. And that's the output of stack collapse. And what stack collapse is doing is it's folding the stacks. So you've got the stack itself is now functions separated by semicolons, and then the counts are at the end. Pretty simple. The value of converting it into one format before we feed it into FlameGraph is now I can write converters for other things as well, like PMC stat. Actually, which Ed Mask wrote. I didn't write that one. But so PMC stat, various other things can now be fed into FlameGraphs. Also, since you have it as in this one line per output format, I frequently toss in a grep setter awk just to filter out some things that the command, like I don't want to see CPU idle. So grep minus v CPU idle before I generate the FlameGraph. So the 3 steps, pretty simple. Profile the stacks using whatever, say dtrace or PMC stat, fold them into that standard format, and then the FlameGraph. And as I mentioned, you can use dtrace stack profiling is for the kernel, and useStack is for user. PMC stat, whatever you do with PMC stat, you can use minus capg to do it in the cold graph format. But you can also use application profilers. Anything that generates a full stack can be turned into a FlameGraph. The stack format I already gave you a quick look at, and there's stack collapse programs for all sorts of things, including like Linux perf events and Mac OS X instruments. And I wrote one for the lightweight Java profiler because I needed it. The FlameGraph program itself, you can customize various things, like change the title and the width and height, and I've been adding some new features so that you can actually do icicle graphs now straight from FlameGraph if you want to flip it. And you can also do reverse FlameGraphs, which I don't have an example from, but so there's the thing I just generated on the OCA. I just fed it into stack collapse and then into FlameGraph. So there's my very, very, very fresh OCA FlameGraph. You can see it's got CPU idle in there, which I don't want. So I can just chuck that out. Okay, gone. Okay, so now I've got all of the CPU samples without CPU idle, and I can mouse over this, and it's going to tell me where things are. I can actually click to zoom. That was added recently. Chrome. If things look a bit wonky, it's when you use the Chrome zoom in and zoom out, sfigs can get drawn a little bit odd, but see how it's doing the font size weird? Anyway, if you don't just click to zoom, then it's fine. It's just because I'm presenting this. So that's merging at the bottom of the stacks, and then the top edge is showing what's on CPU. There are a few types of issues which helps if you flip it around, and if you merge the top of the stack. Like say you spend a lot of different code paths and in mutex doing spins, and you actually want to merge the top and then have the bottom separate. And so you can do that. I only just added this. Other people helped reverse the stacks. And what did I end up calling it? It's a reverse and inverted. I don't know what this is the first time I've done it on the OCAs. Oh! Yeah, so we now merged on the top instead of the bottom, and The biggest guy is mutex lock sleep, which is not really surprising. That was at the top of the stack, so that was on CPU 8% of the time. And then now I can navigate downwards. I can actually just click on that. Yeah, the font size looks weird because of Chrome Zoom. But now I can go downwards and break apart that 8%. So I can see that 1.38% was in T4 Ethernet receive. We've got 2% in TCP LRO flush. Oh, what's this guy? Oh, I can just mouse. No, that's fun. I can just mouse over things. I've got we end up in VM page free to queue, in free memory. Anyway, so TCP input, cool stuff. I demoed filtering already. CPU flame graphs. So that's what I've just been demoing, and that's just where I'm profiling the CPU, just to visualize what's going on. So A's on CPU, I sample the stack as A runs B, I sample the stacks now B and A. When I block, we're not sampling anything. It would be neat if we could. That'd be nice. Anyone know a way to sample stacks when you're not on CPU? I have not seen a profiler built to do that. But it would be kind of neat. A problem is you can have lots and lots of threads that are asleep, and so it gets expensive to do it. On the other hand, it would be nice to have like just a low frequency off CPU profiler that could do this at like 10 hertz. That would be interesting. Anyway, I digress. CPU flame graphs, already demoed some of these. Another one, just to show you what's possible. Let's go back to the ones I loaded earlier. With this flame graph, I'm using dtrace to capture not just the kernel stack, but both the user and kernel stack. I guess why not? You can just capture them both at the same time. And what I've done is I've inserted, there's a one-liner which I've got in the slides, I've inserted a separator so you can see the crossover between user and kernel. Adrian? Which one? So procstat dash. Procstat minus KA.
That's all the threads in the stack, the kernel stack for each thread.
Oh, and it's doing it in single line format already. Very good. Just need to set these out to be like semicolons. That would be cool.
If you add 2 Ks, you might be able to get the offset, which might give you storage as much of what you put.
So yeah, just on the first, that's a good suggestion. I will do that. But just on the first pass, what character is that going to be? Like 60 plus? I can't do that. Did I chop that off? Give me a character. Okay. How about 48? Yeah, I know. I should do TR.
Looks like Bernie just rip out.
Yeah, I just stripped it. I know. Okay, where am I going to stick? Use a local CCS data. Okay, so it's only a single sample. So what I want to do is capture a few of these, just because you need. The latency is a little bad. So this is really dodgy, but in capturing a few of these, because a flame graph is built up of samples, not a single snapshot. So you can't just like run JStack on Java or do one. You do want to have like at least 100 samples in here. I went to 100 samples. I'll just do a few and see if this is going to work. Okay. Right, so far so good. Yeah, I wish I could U encode this one and put through my paste buffer. What do I call off one? Now I missed sample counts at the end, but I can just whack that on. You know, watching the output, I know I missed something. This wasn't too big, was it? Oh, 3. Okay, good. Yeah, it's going to take 20 seconds. So most of it's there. What I need to do is add I forgot to add a number on the end. Flame graph will join these together. Like, look how it hasn't aggregated them up, but that's okay. My flame graph's going to do that for me. So now I've got this guy. Now I can just add 1 onto the end of everything. I'll give it a color palette, make it blue because we're looking at block design. They'll be nice. Hooray! Wow, that's pretty cool. So, 606, again, discount the varied font size. I know that happens when you use Chrome to zoom. But we've got 606 samples. We're in XFast system call.
It's actually inverted because of the way it's set in.
Oh, thank goodness we've got this. That looks better. Now we end up in sleep queue, MI switch. Oh, wow. So is this blocked or blocked and running?
Blocked. The ones that are running say running. They don't say. There's a way to make it do running.
Okay, so if this is just blocked, that's great. Like that's cool. That works for me. So now we have our off CPU flame graph. So I'm just showing you, add a title to it. Off CPU flame graph and 606 samples where we were blocked on a context switch, sleep queue, catch signals. We've got this guy in here. So just click on that. That was nano sleep. So something is deliberately sleeping. It's great to just detrace who's sleeping because then you find out that let's detrace who's sleeping. Oh yeah, I have to. Because often you hope it's like commands that are supposed to be sleeping, but it's some of the easiest performance wins are when you just say don't sleep. I know, it's great.
If you care about the distinction between activity and productivity, then...
Ah, LCDD is sleeping, calling nano sleep. And SV scan. Okay, so we're probably looking at LCDD a lot there. Okay, fine. So you get the picture. Really, really cool stuff. It's oh, look at this tall guy. Alrighty, so sleep QA, VM, alec buff. Oh, do we have a sleep in the virtual memory system? Did we need to?
If you're paging in.
Yeah.
If you're paging in, you end up blocking because you're waiting on. All right,
Yeah.
because we're doing. If we go, because it's a fault. We're faulting. Fault FFS read sleep. Cool, and I caught that just by hitting enter on what was it? Proc stat minus K.
Yeah.
Proc stat minus K. All right, good. Excellent. So, finishing off the CPU stuff because we just discovered some things that are cooler. So you can do both stacks at once. That's neat. What I want to do is add a feature so that I can colorize user in green and kernel in red or something like that. I haven't done that yet, but it won't be hard to do. Demo slide. Yes, I've done some demos. CPU commands I've got in the slide deck. So kernel stack sampling at 199 hertz, and then user stack sampling at 99 hertz. If you care enough to learn dtrace, then you can see there are subtle differences. So kernel stack sampling is S stack, user is U stack, and I'm changing different tunables, and I'm testing on different. That's the user program count, and that's the kernel one. So there's subtle differences in there. Yes.
Why 199 hertz and 99 hertz as opposed to 200 and 100?
Well, because I don't want to sample in lockstep with something and have inflated and deflated sample counts. So at least I investigated this on Solaris because it has high resolution cyclics, and experimentally did this enough times with 100 hertz and 1000 hertz to show that you can indeed sample in lockstep if you're really unlucky. So that's why we always pick like just something slightly off so that you have a better profile.
If you remember, FreeBSD used to have stat hertz, which was specifically done so that you would be able to, gauge the CPU scheduler in order to get more kind of stuff. So
Cool. CPU used to have, FreeBSD used to have
that's stat hertz.
stat hertz, so that was a separate hertz for statting.
Yeah, but it's not showing up in interrupts like it used to though.
Cool.
The
We
original,
still have the interrupt for scheduling.
the original stat hertz came about because we used to have to charge for CPU time, and so students who had no budget learned how to hide behind the clock so that they could get like 90% of the CPU and be charged for almost none of it.
Oh, wow.
So, but the early machines didn't have but one clock on them, so the way we got stat clock was we took a TTY line, looped back at 9600 hertz, and used that, just continuously send characters round and round and round, and use those interrupts for our stat hertz.
Excellent.
Wonder where it came from.
So there you go, stat hertz. And what was the system clock rate at the time? Was it 60 hertz?
100 hertz.
100 hertz. So students were like running something at the start of a
They were
window, and
they
then
were running off the real-time clock, and then they would make sure that they didn't use a hundredth of a second before they went back to sleep, and
Right.
wait for the next real-time clock to come in.
there you go, stat hertz. Excellent. Thank you. That's really interesting. So this is our version of stat hertz in dtrace, just so that we can defeat programmers. I do have in the slides how you do those dual kernel user stacks. Basically, if you insert a line that has a dash, then it turns into, I just color it green automatically. So you've got all those commands. All these flame graphs I'm showing you are built on FreeBSD as well. Memory. So for memory tracing, I've drawn a nice diagram to show there are 4 targets that we can attack. So if you want, you can trace at the allocator level, like malloc free, realloc, calloc, and friends. Or you can trace breaks, so when you extend the heap. Or you can trace mmaps, munmaps for the other purpose. And so depending on the allocator, it may have a hybrid. So for like many of the GNU allocators, you'll do mmap, munmap for very large allocations, and then just push the break around increase the break for smaller ones. So it depends on what the application is doing. And then the last one is page faults, where you can actually trace when we go to the VM system to do a page fault. It's interesting to look at their different targets. So tracing these guys will explain virtual memory growth, and then tracing this guy will show you the RSS growth, so actual main memory growth. Usually, I care about tracing that guy. Tracing that guy will show if you cast the user level stack when you do page fault, you will see the user level stack that faulted it, that consumed memory at the time. That may not be the same stack that did the allocation. So if you trace here and here, you can actually see the allocation stacks. And then you trace down here, you're seeing the usage stacks. So just as a caveat, but it can be interesting either way. Here's VM fault kernel stacks on FreeBSD. It's a little boring. I probably wouldn't have even done a flame graph for this, but I can see that we've got a lot of sysctl, TCP, we're in TCP, and we're doing VM map of wire. So means we're running netstat?
Yeah, that's what's going to call that system.
So netstat is doing that.
Yeah.
Okay, all right. This is not very interesting. It can be done. I did check on the OCAs, and it was not interesting right now either. But you may have a much more interesting workload. So it's a matter of using the dtrace FBT provider, VM fault. So when we're actually doing the fault, and then looking at stacks. I think if I do it right now, yeah, that's not hugely interesting. And I don't even need a flame graph for that. Oh, we're doing a lot of faults in TCP.
Yeah, that's that minus PTCP, but that shows the address of the list of sockets. What that, what's on TCP.
Oh, because it's doing a TCP
Yeah, it's
TCP
listing
list.
all the protocol, PCBs.
So who's doing that? Let me throw in an exec name. Did I catch it?
That is BSNPB.
No. Let's do file read from Perl. See, now it's gone away. I should have done this earlier. Now it's hiding.
Yeah, just back to last and look. It's just gonna
What was the one earlier? But if we know it was, what was it, TCP plist?
Yeah, PCB list.
That one?
Yep.
So let's do the exec name and the use stack to see the user level stack of why we're in there. Yeah, it's not going to happen now. It's hiding.
Go next step, that'll blow everything up.
A netstat?
Yeah, seriously, NetStat is extremely aggressive with its locking and causing
All right. So. Okay, fine. So it is netstat. I mean, netstat had died by the time it printed out the stack, so that's why you get hex. So memory commands, I did in the slides show how you can do the fault flame graphs, if that's more interesting for you. There are overheads. This can happen more frequently than the previous one, which was the CPU sampling. So be aware of what you're doing when you do that. This guy is another target, and at this point you probably get the picture. Any event that happens in the kernel, I can then cast the stack trace that led to it and then look at why. And it's more interesting if you have lots and lots of stacks, so it gets complicated. So here we've got yeah, thanks. It's I can see I've got 1,000 I/O were issued through VNIO faults, so VN write, UFS strategy. That makes sense. So that's a write code path. FS write, cluster write. And I've got a lot of these other guys in Geom. A lot of these hex addresses, I don't know why they're not translated. Is Geom IO schedule down calling some dynamic code to issue things? So I haven't looked at that yet. So dtrace, just a different probe, same strategy, get the stacks together and then feed it through flame graph, and I can generate a flame graph. Off CPU gets more interesting. With off CPU, the CPU flame graphs kind of can solve any problem. So if I'm executing on CPU and I have a flame graph, I can navigate around this and I can explain generally why. But that's only executing. So other thread states, so if we're doing paging, if we're runnable but we're on a run queue, sleeping, waiting on a lock, blocked, waiting for work, they're not part of that profile, but they're part of our procstat minus KA profile that we just did. So off CPU profiling lets us attack everything else. This is an off CPU time graph that I created earlier, which looks remarkably similar to the one we just created earlier today. See, I ended in MI switch. See, MI switch, sleep queue, cache signals. See, it's the same stuff.
How did you create that one?
So yeah, I created that one using dtrace. Let's look at these side by side. Look, they're kind of, oh, that's interesting. There's one where I'm actually doing both user and kernel stacks off CPU. So it's created using dtrace, and what I'm doing is I'm tracing the off CPU to on CPU events. And then doing a timestamp. So when you go off CPU, set a timestamp. On CPU, do the delta, and then associate that with the stack trace, do the sums in kernel, everything else is the same. Warning, this has a high overhead because we're tracing on and off CPU, we're tracing scheduler events, and that's going to cost. And so while this is wonderful, it does hurt to do. And in fact, when I was running this last on FreeBSD, I was getting dynamic variable drops, which is why you increase the dim var size, just one of the dtrace tunables. So I can do off CPU tracing, and I've done this a lot before, but it's relative to the context switch rate or scheduler rate, and it can start to add up. Like dtrace is fine if you're doing 1,000 events per second and less, pretty much fine. If you're doing more than 10,000 events, you start to measure you start to notice its impact. If you're doing more than 100,000 events, then you're going to notice. If you're doing more than 1 million events, then like seriously going to notice. It could be eating like 30% of all your CPU or 50% of all your CPU just to do it. So, and can you get into that ballpark with tracing scheduler events? Yeah, you can. Scheduler events can get to millions a second. So that's why it's very neat, but it's I wish there was a better way to do off-CPU analysis, but Adrian just gave it to us, which is doing the procstat minus KA, which is interesting because, so this is the one I just did earlier. I already know one difference between them. If you look at the dtrace one, you think, well, this is cleaner. There's fewer stacks than the procstat minus KA one. Dtrace is relying on an event to happen. So if I begin running dtrace and you've already gone to sleep, I'm not going to see you. And if I control C before you wake up, I'm not going to see you. Whereas with procstat minus KA, it's walking all the threads. So I'm going to it's actually a more complete off-CPU flame graph to do it using that approach. So now I just need to have a subset, like while true, procstat minus KA, sleep 0.1, and do that for a minute and get a decent profile. It's really interesting to go down that path as well, because on CPU issues, which are very common, you solve some using top, you solve many using CPU flame graphs, and the remainder you can attack using performance counters. But at the off-CPU issues, there's many that aren't straightforward. You can get some with ISTAT, SciStat, and log profiling, and off-CPU flame graphs. And now off-CPU flame graphs are cheaper. But as it turns out, if you do spend time with this off-CPU flame graph, you'll find that it's not really answering the problem. So here I am in sleep Q times wake sig, and I was there on 606 samples. What am I sleeping on? Like that might be important. So it visually looks very nice, but like I've sat down to solve problems with it and realized that off-CPU flame graphs may solve 20% of the problems off the bat, because it's like, oh, I didn't know I was blocked on that. But the remainder you can't see in the stack. Adrian's going to solve it. I've got more slides. I will solve this. Yes, what's the solution?
No, it's not a solution. It's the thing that just occurred to me is if we append the weight channel at the end of the stack, right, then you have another unique thing that we could another stack. Other things are sleeping on the same weight channel.
So the weight channel, is that a unique ID or a state?
It's a string.
Oh, is it a unique ID or a state?
It's not usually an address.
An address.
Yeah, it's not. There may be multiple different points that weigh on the same channel, but it's purely informational. So, but it is a good thing to distribute on.
But it shows up at the top.
Yeah.
Telling you why this process isn't doing something.
What's it called? What's WChan?
Find a call to like C-sleep or something.
Is it this guy? No.
No. Yeah, look to like sleep. It's just a void star.
Oh, it's a void star? No. What's the type?
It's a void star. Look for T-sleep. And you see how there's W message and there's Chan? And Chan is a void pointer, which is the actual pointer that you pass to wake up to wake somebody up who's asleep on something. And W message is a string. It's a const char.
Yes, yeah, I've been down this path before. I wanted you guys to mention it because I needed to see the code. Yes. So I can use I can use that guy to associate the stacks, and I can use that guy to just for more informational stuff about this is the general grouping of why we're blocked.
Except you'll find that like all of them are in select. And
All of them are in select, which is really boring. So we actually need to know what the guy that wakes them up is.
or what's really useful is to know which, if you're in KQ, you want to know which items are on my KQ that I'm waiting for. If I'm in select and I've called for select, which FDs I'm actually waiting for. I can do that in KGDB and have.
Yeah, but I'll try to solve it in a second. Yes.
It's actually the strings are more useful than I think people are making out. For example, if you're a badly behaving ZFS box, you'll see all of your stuff sleeping. For example, ZIO pointer CV. And so it's actually, it's not always the front process is sleeping in sleep, in select.
Right. I mean, Adrian said the strings can be useful, and I'm sure like we'll see them be set to very useful things in here, like there you go, VM hold VM. No, it's great. Please put strings in the kernel. Lots of strings. I like strings. I've detraced them. Like they're easy to get out. So the more strings, the merrier. FreeBSD is nice because you have TD name for threads, which Sass doesn't. But so chain graphs is the last section of this talk, and this is where, in order to really attack this problem, you need to walk the wakeups. So I've got offc. Why do I have this curly thing? This is my spell check.
That's not a word.
You've got yes, not a word. You've got off CPU time. That solves some problems because it's a surprise I was blocked on it. But often you need to know the guy that woke you up and what they were blocked on, and often you need to know the person that woke them up and the person that woke them up, and you actually need to walk the chain all the way down. So we can do this, and I have not done this. This one, I'll show you the potential. I've not done this on FreeBSD yet, but I just need to sit down for a few hours and get a prototype happening. But I'll show you what my attempt at doing this is. So this is the only example I had from a different kernel. This is doing it on SmartOS. So I've got my off CPU stack, and I've included the object that we're blocked on, which is which is what we just looked at. What was it called? The
Wait channel.
The wait channel. Yeah, not the wait message, the wait channel. So you print the stack and you put the wait channel object, and then what I'm also doing is I'm tracing the wakeups. You trace the wakeups and you include the wait channel object there as well. And then I've got some a program which I lost and I need to rewrite, which I should have put this. Everything should go on GitHub, and then I will not lose it. And then it will associate together the wait channel objects. What I've done for this flame graph, this is my block stack. Above it, I've printed the wake up stack, and you can see how I've associated together basically the wait channel. On FreeBSD, I'll include the wait message in here as well, just because it will be informative. And I printed this stack in reverse, so you can see that's what this shows. The target thread is why I blocked, and then in reverse, I woke up this guy, I woke up this guy. And it's connecting together all of the wait channel objects. And the width is proportional to the amount of time they were blocked waiting. And the particular example I've got is, this is SSHD is blocked on a conditional variable. There are two paths that wake it up. This path over here is, I'm being woken up by TCP/IP, which is not a surprise. A packet came in and I was blocked on that. This other path says I was woken up, remember this is SSHD, I was woken up by string write. All right, so the write syscall woke me up, and if I go back up, I see it came from vmstat. Vmstat did a write syscall which woke up my SSHD, and the reason is in a window I'd run vmstat space 1, and that was updating the screen, and it's doing the wake ups, and so associating them together is fantastic. So why is SSHD not running faster? It's because it's waiting for vmstat 1 to emit a line of output. And that associated, but you don't stop there. What's vmstat waiting on? Vmstat's waiting on this guy, which is doing a timer. And by the time we go up to here, we're going to metal. Because vmstat 1 is actually creating a timer and then waking itself up. And so I found when I created these chain graphs that all roads lead to metal. So metal wakes up everything. So it's going to be a timer or an interrupt, and then you have all of the stacks, and then it comes down to where you've blocked for off CPU. I think it's really exciting. The problem is the overhead is, at this point, to do this, you have to trace all the schedule events and all the wake-up events, so the overhead becomes pretty crazy. So just managing that and fine-tuning that is something that would be exciting, and I keep trying not to put my hand up for. So maybe I should try to help with that in FreeBSD, is getting that stuff to work faster, so the cool things like this are more practical that we can do. And I've called it grand unified analysis. Imagine being able to do both practically, so we can do CPU flame graphs and chain graphs, and then combining them both, so we have a unified means to attack any performance issue. There is someone doing something similar with LTTNG and Linux. Instead of doing stacks, he turns a stack into like a single reason, because he's dealing with very complicated dependency wake-up graphs. But it's very interesting work as well, and if you're into this, you should read his presentation as well. And lastly, I just wanted to mention some other topics in flame graphs, and I'm up to 45 minutes, I'm sorry, I did start a bit late. CPU counters. PMC stat is fantastic and gives us access to all sorts of things that are going on inside the CPU. I had this diagram yesterday. And so any of these can be a source of flame graphs as well. So I can do a flame graph for cycles, instructions, cache misses, and so on. And I came up with a great one last week, which I've always wanted to do. And this is where you have the normal CPU flame graph.
Sorry.
Oh, you're laughing at what's being
I know
highlighted?
exactly what you're doing, and it's sort of appalling that I drew just by looking at the graph. Go on.
So this is a, let's make sure. Okay, I clicked in. This is a normal CPU flame graph. So the width is proportional to the number of times that frame was present in a sample. Basically, you're looking at why is percent CPU 80%? That's why, proportional. And it's because this guy was on the stack that much, and so on and so on. But what a flame graph does not answer is, when you were on CPU, were you stalled? Were you doing stall cycles, or were you actually retiring instructions? And so what I did was I used PMC stat to record the cycle count at the same time as the stall cycles. It's sample-based, so it's like every million do this. And then did a differential flame graph, which I only pushed the code last week, so that I can color, the darker blue it is, the more stall cycles it was, and the more red it is, the more instruction retires it is. It's basically the color range is mapped to CPI, cycles per instruction. And so if I zoom in here, so here's my, thanks Rem, here's my FFS read, and VM page alloc is quite blue because it's walking a lot of page structures in memory, and that's going to have a lot of stall cycles. And mutex slot sleep is quite red because it's a spin loop. So this particular flame graph was not very amazing or new, because we would kind of guess that based on without that information. Scott Long, who's already dashed for the airport, is working on that stuff already. Was already working on that stuff already. The stuff that's highlighted the most in the CPI flame graph. So really cool. And of course I want to do the same thing for like cache hits and misses and all sorts of other PMC sources. Flame charts, in case you run into them, Google was inspired by flame graphs and put flame charts into Chrome. It's different, and I'm glad they renamed it, because they do the passage of time instead of the population. On my flame graphs, the x-axis is just alphabet sort. It's not the passage of time. And if you sort by alphabet, it merges very well. Google did passage of time. And I've got a website where I do list out everything else which has been happening. And then the last thing to mention, if you think this sort of interactive SFIG is fun, a great way to browse performance data. I do have another one on GitHub for flame graphs. It looks a bit washed out, but for heat maps. So I can pipe dtrace output into another Perl program and generate an interactive heat map. So that's my talk. Lots of different types of flame graphs. And thanks, Adrian, for his help. I now have a much more efficient way of of doing an off-CPU flame graph based on procstat minus Ka. So, thank you. Any questions before we break for snacks? Yes?
So personally, we love flame graphs. We've been using it. And I don't know, like once we found it, like we wouldn't do anything else. So anything else, first we do flame graph to figure things out.
That's great. It's great. Flame graphs first before anything else.
Yes, and it's easy. But I think like the thing that you're mentioning, the chain graphs and like linking, that's where I think like a problem is. I think that's the next step. If you can make it as simple as flame graph that you can include it and do it all the time, it will be super awesome.
Thanks. Yeah, I mean, I really think if I can get the chain graphs to be low enough overhead to just a tool we can run, it gives you a quick way to attack all the blocked issues, all of them, like whether it's locks, sleeping on, whatever. So yeah, I am really excited by chain graphs, and really excited I have dtrace on FreeBSD with the very interesting workloads at Netflix to continue doing this work. Yes.
During these videos, can these be given to the writers working on Jenkins so we can have these as like a daily kind of thing?
Yeah, so a number of people have done them as daily flame graphs for doing non-regression testing. In the Node.js community, one company was created so that every time you did a putback of Node.js code, it then repeated a performance test and created a flame graph. So you can go back and look at a flame graph for every single commit of code.
Which graphs would you use?
So I would do a CPU profile flame graph, CPU sample flame graph. But now that I've done the code for doing differentials, see, I actually wrote this for doing differentials. So if you gather the dtrace profiles, and I put it all on GitHub, so you use the diff folded program and feed it into flame graph, and then it will color red on the code paths that have increased and blue on the code paths that have decreased. So I think if you want to set up Jenkins for this, or you want to set up crontab or whatever, you want the daily flame graph, but you also want the daily differential. So that if something odd has happened, you can bring up the differential flame graph and then see what changed.
You instead of doing it like stall cycles versus hot cycles, you do it between the 2 days.
Yeah, just profile 1, profile 2.
Yeah, no, I'm just trying to figure out how to like innovate it. So,
I mean, the code is just very simple.
It's basically at the start of Jenkins run, you fire off TNC stat or whatever, do it. When it completes, kill it off, let the data.
we have to launch all these locks or defense.
Well, it's whatever program, wherever you run the test, just before you start the test, you run off the dtrace.
Yeah, so dtrace is on FreeBSD. It lives in a world, like, its output is text. Flame graphs all process text. It's all pretty straightforward. It's just a few commands. We've set it up on the FreeBSD OCAs. So we've got a cron tab that will generate flame graphs and a script under user local that generates flame graphs.
What's OCA?
It's the Open Connect appliance. That's what Netflix has for streaming. Other questions? All right, thank you. I'll post the slides online, and you're free to ask me questions afterwards.
Yeah.